This is the second part of my video on paleosols, and in it we're going to look particularly at the Llano Estacado. We'll look at the paleosols and some really intriguing finds up above those. I hope you enjoy this trip to the high plains. This second part of my video on paleosoil, as advertised, will focus on the Llano Estacado flat plateau in eastern New Mexico and West Texas. It's pretty big. It's about the size of the state of Indiana. I want to review just a little bit. In part one, as with this slide, I showed some of the most popular young Earth creationist interpretations of the rock record. I showed how with what is zone 3 is what they would interpret as the rocks that were deposited by Noah's flood over the course of 1 year. And the bars kind of with the light blue top and the dark blue base put out by Dr. Tim Clary from ICR and Dr. Andrew Snelling from AIG are scaled in days, make it up for that 1 year period. And we can make some estimates then of how fast things happen during that 1 year flood. But we also see the zone 4, which would be those rocks which were deposited between Noah's flood and Abraham over the course of at most 450 years. And then those rocks in zone 5 that were deposited after Abraham over the course of about 4,000 years. Okay. And we saw paleosoils within that rising interval, or rocks that they would call from the rising interval that had good paleosoils in them from the that package, both in New York and in places like China and in Texas. But then we zoomed in on this interval up near the top, and we did show that with the next slide. The zone up at the top would be that interval that shows when the Ogallala Formation was deposited in terms of its stratigraphic position. It would be during the late Miocene and Pliocene. And young Earth creationists would also recognize these ages. Stages differ in terms of how long they believe they lasted. They also differ among themselves in terms of whether the Ogallala Formation was deposited during the flood or after the flood. Okay, and I showed a map before, but just to make sure you have this picture in your mind of the Llano Estacado, and I put in some of the important cities in the area. Lubbock and Amarillo are probably the largest. And I put in the town of Dora because that's where I'm from. And that makes it very important, at least to me, even if it is just less than 200 people there. So look at this again, show us some of those locations. We will look at a number of examples from Paladoro Canyon. We will then look at later at Blackwater Draw in New Mexico. And then we'll also take a look at the Alabates Flint Quarry and its relationship. It's very close by this. Now we'll look at that second part of paleosoil. We'll look at the Llano Estacado. The Ogallala Formation in terms of the geologic periods or epochs that we were looking at, epochs being parts of periods, then is being from the late Miocene to Pliocene in age. Most geologists would say that this was deposited over about 10 million years. So let's look at the Ogallala Formation just to tell you a little bit about it. We'll look at it kind of in map view. This is a thickness map, so the thickest areas are in blues, and you can see that the thickest area in this is up in Nebraska. In fact, that's where the formation was named, from the town of Ogallala. And actually it received its name from apparently the Oglala Sioux Indian tribe. So that was named, the town was named after them. And then the formation was named after the town because geologic formations are named after location. So let's see what we can say about it a little bit. We're going to go describe it down in the Llano Estacado, which is that southern kind of lobe of this. Ranges over a huge area, but down in the southern lobe, what we see again is a formation that's setting on top of what's called the Dockham group, a Triassic group. Above that, you have an interval of sand. It's very important to us because that sand is an aquifer. it holds a lot of fresh water. Fresh water is a very important thing to have in this part of the world. You know, it says that so we've got a thick sand, and then there's a little thin caliche formation up above that. And then we get into the Blackwater Draw formation that's above that. That's where we'll look at as well. So this is kind of the overall distribution of it. So now we're going to go to Paladuro Canyon. And this is kind of a picture in Paladuro Canyon. And you can get an idea of what the rocks look like there. The bottom kind of red interval is called the Quartermaster Formation out of Permian. So this would be in the late part of the Paleozoic. Andrew Snelling would call the rising waters, maybe deposited over just a few days, in his opinion, maybe 1 to 5 days. We'll look at the Quartermaster a little bit more later. And then you get into the Dockum group, the Triassic age. So this would be early in the Mesozoic, early in the days of the dinosaurs. And Tim Clary, Dr. Clary would say that this was all part of the rising waters. And then you would get into what he would see as the receding phase within that Ogallala formation. So the question then between these guys would be, is the Ogallala formation a receding phase, or is it part of the post-flood deposit, depending on who you're looking at? And it's really just a real thin level layer up on top of this. Dr. Clare would say, well, that was deposited in less than 40 days. We'll take a look at his opinion on that. And Tim Clary has more time to do with it. The post-flood deposits overall could be 450 years, but probably this little portion of it would just be at most 100 or 200 years. Then you get a very thin little wedge on top of that. That's the recent deposit. That's 4,000 years of deficit. That we can kind of all agree on. So now let's take a look at what some of the things Dr. Clary is saying about the Ogallala formation. He's put out articles such as this one, which is on the Institute for Creation Research, or ICR website. This says the Paladuro Canyon rocks showcase Genesis flood. What he's basically going to do is use the Ogallala formation to do that. So this was written in 2018. He also included it in his book in 2020. And he uses this. Let's take a look at the Ogallala in the Paladuro Canyon to make this case. He's saying again that the part of the receding phase would go all the way up through the Ogallala formation. And in particular, he's interested in that basal part of it, that's sand. And what he's going to take on that sand is he's going to say, to use a quote from him, secular scientists claim these are deposits from rivers, but a receding mega flood explanation better fits the broad extent of the Ogallala. And we saw the broad extent, there's no dispute about that. Then he says, how else can a blanket sand spread across thousands of square miles with no evidence of river channelization? This is something we can test. Is there evidence that that sand was deposited by a river process? One of the things that he sees in the Paladuro Canyon area that convinces him that this has to be part from a sheet deposit is the fact that the Dockum group and the Ogallala formation are essentially parallel in this area. Does that tell us that there wasn't any erosion about this? Standard geology would put a significant time gap between these two. We would call that surface of the time gap an unconformity. Okay, so what is an unconformity? The surface of either non-deposition or erosion, and the beds above and below it can be either parallel or they can be at a different angle to it. In fact, it doesn't say an angle here makes him say that this is not really an unconformity of any significant time. But the time gap isn't really dependent on whether there is a difference in the dip of the beds above and below this unconformity surface. That tells us a lot about what the tectonic history is and what the folding history of the rock is, but not a lot about how much time it's missing. Very little time, in at least conventional geologic terms, can have a sharp angular difference between them at times, but a great time can also have very little change. Is there erosion in between these two? It's not really apparent in the Palo Canyon area that there is a lot of erosion between the Ogallala and the Jocham group. Well, let's take a look at a different area. For that, we're going to go into New Mexico, near the town of Grady, near San Juan, New Mexico, up toward Tucumcari, if you're familiar with Tucumcari. So here's what we see here. In the bottom left picture here, you see the flat plains of the Llano Estacado, and then you see that caprock edge of it. It cuts in here, and you see the erosional surface that's cutting into the caprock. And here's a picture around one of the road cuts, right in that area. And what you would see is an erosional unconformity cutting down into a very irregular surface as it cuts down into the Triassic rock, which are the Jocham group in Texas and the Chinle Formation in New Mexico. It's like there's a great fault line between the two, but really it's one formation, one unit. That the rock in it is made up of sands and gravels, just like you can see in the little incision that's blown up in here, where you can see the pebbles and stuff from a typical type of stream deposit in there. And to me, this is very convincing, and we do have, it does show that in places that surface between the Triassic rocks and the Ogallala Formation is very eroded. Well, what about the idea of channelization otherwise? Is there more evidence? For that, I want to take a look at the northern part of the Llano Estacado, the area that's in this red, and we're going to take a look at the thickness of the Ogallala sand. If we look at that thickness map, again, the dark blues are the thick areas, the light blues are thinner. And what we see is the sand that's variable in thickness across this. The map is available in Texas. This was produced by the Center for Spatial Technology in 1990, put out by Texas Tech University. And you see the thickness variations across this. And if you look kind of between Lubbock, Texas, and between this yellow dot over here, that's the Blackwater Draw, near Clovis, New Mexico, that's labeled on the map, then you'll see there's kind of a winding pattern of the blues in here. A sinuous, weaving, kind of meandering pattern of sand thickness. Kind of with that type of sand thickness variation really looks like a river deposit. Looks very conclusive on that. And it's also the case to be helpful because when you look over in the Blackwater Draw, that location is where they found the mammoth bones and the human artifacts. They were found while they were mining for river gravels out of the Ogallala Formation. Those river gravels, of course, were used in making concrete in the area, so this was a mining operation. So if we follow from that potential river deposit down that sinuous path, we would come near Lubbock, Texas. And what would we find there? Well, Dr. Dale Winkler from SMU has done a study on that. He did an outcrop study in that region in 1990. And here's some of what he found. This is a schematic cross-section that shows that there's an erosional surface at the base of the Ogallala Formation and a whole series of nested channels from a river system coming in this area. You have the yellow channel fills in this. You have windblown finer sand, and you also have this light blue in here, which is caliche. Of course, there's a very extensive caliche that comes across the top, but there's also caliche down in the end of the canyon. We'll talk about caliche. So hang on to the thought. There's some of that not only at the top of the Ogallala, but down in it. So this looks like a river system. My wife and I took a little field trip over there, and you can get into this area looking at an area called Buffalo Springs near Lubbock, Texas. And here's what we saw there. Looks like a very classic type of fine sands that are being deposited by a river. You can see a lot of the channel forms as the little streams would have meandered their way and varied in their direction and orientation a little bit with time. A wonderful little river deposit. And to me, that's very conclusive that this is deposited by a river. You see that in the thickness, you see that in the gravels in New Mexico, and you see it in the expression over here near Lubbock. We don't see that type of expression up in the Palo Duro area because that's not where the main rivers were flowing over there. That's in a side area. So we're going to look again at these predictions. Keep coming back to the amount of time that is available. It tells you something about the type of processes that would be found in the sediments given the predictions that we have. From the ICR's point of view, the Ogallala Formation would have been deposited in the receding phase over approximately 30 days of deposition at most. These are the sands that Dr. Clary wanted to make the blanket sand, so we see the river deposit. And the river seems to be about the same size as the type of river that we see flowing now in the Brazos River. So an ancestral Brazos River kind of flowed through between Clovis, New Mexico, and the Lubbock, Texas area. And that's kind of a neat picture that way. How long did it take those river deposits to form? In an overall sense, Dr. Snelling has 450 years, maybe 200 years or something. But those type of deposits, as they form today, they would reflect hundreds of years or thousands of years to develop that type of deposition. That seems to be a very reasonable estimate. So now it's time to move from the sands of the river into that caliche deposit. That's a paleosoil. That's what we're supposed to be looking at in this talk. This is a picture of the caliche, the white limestone that was deposited as a paleosoil in eastern New Mexico. This is near Llano, New Mexico. My wife's aunt happens to have some farmland there, and this was taken just not far from her house. And in fact, we'll be looking at some pieces of caliche that were picked up right along this road. They were mined out just off of this location right here. So we know where they came from, and we can tell a lot about the process by which they were formed. When we're thinking about caliche as a paleosoil, we want to go back a little bit and see how do caliches develop, what's happening. We used the model on the left before to kind of show the different soil horizons, and you can see a photograph from the University of Idaho of an active caliche deposit that's forming today. And you can see where there's a concentration of whiter sediments down there in the basal part of this particular exposure, and some lighter colored rocks up above it. All of those are called B horizons, with a very thin section at the top called A. How do they form? I mentioned before, you can have different ions that are moving down, leached down by groundwater into the system, and that's what's happening here is that you've had calcium ions move down the system and then deposit as calcium carbonate. It's important to realize that this had to form in relatively semi-arid conditions. If it formed in a humid condition, the calcium would have completely washed out of the area and it wouldn't have been preserved this way. But if it's too dry, then you don't get much calcium carbonate down. You don't get the water moving and you don't get the stuff washed down. So that, again, this reflects kind of a period of a pretty stable climate or a long period of time where the calcium carbonate has concentrated. Now, this is an example that's from fairly recent Earth, and you can see that the calcium carbonate, the main layer of calcium carbonate, the main caliche layer in this case, is just a few centimeters thick. And parts of the Llano Estacado, they get a little bit thick. So here we are in the map in the Llano Estacado, near the Lubbock area again. We're going to look at that caliche deposit. And you can see they get pretty thick here. This would be caliche that's formed in a whole bunch of soil zones across this area. Not just one, but multiple soil zones. The most resistant ones being up at the top. That's the main calcium carbonate that goes over there. You can see kind of one 6-foot tall geologist down there. That would be me. And I'm pointing out some of this, but that's a lot of caliche developed, suggesting that there's a long time that was involved in deposits again. We see some other features we need to take a look at. Other indications. So this is a picture near Buffalo Lake, near Lubbock. And you can see a lot of kind of white layers of caliche that have been moved down into the rock, mixing in this way. Those I'd interpret as rhizoliths, root structures that developed in this area from ancient roots, calcium concentrating around those. And, but there's another option on that. Maybe they're not root structures. Maybe they are ant nest ichnofossils or trace fossils. And this has been, some of these have been identified up in the Ogallala Formation up in Kansas by John Smith and several other authors who published this. And here's what they found. A similar type of situation with lots of these vertical layers. They identify these as being formed by ants who are found down in their ant nests. They do kind of have a lot of areas where they kind of bunch together or thicken up and widen out, stuff like that. And that may be an indication that, and you can see that these are forming kind of in three main layers. We had a number of different paleosoils, and some of these would have developed these ant nests. Is that what's happening in the Buffalo Lake area? Well, that's certainly a possibility. You'd have to do more work to be able to be for sure, to be able to tell the difference between these two. It's possible that there are some roots and some ants in the same type of an area here. So what does that tell us? This was a soil that was there for a long enough time for a lot of ants to move through it. And this is just one particular little zone in this. Soil studies recognize 6 different stages of calichification, forming these caliches in this area. It's hard to tell exactly how long each one took, because some of these, sometimes the same horizon can be at different stages in different parts, depending on the local conditions. But you can see it moves from the part of just having some carbonate coatings and little threads of carbonate over a stage 1, more nodules, the nodules coalescing, make a solid bed of this. And then eventually you're beginning to have this laminated or layered, thin layers of limestone up at the top of it. This way it's getting very plugged, cemented together. Stage 5, you've got these things called physoliths. Physoliths are these features that have lots of lamination to them, where groundwater soaks down through these things and cause different grains and features to be coated many times, many layers of calcite. And eventually that all gets broken up by stage 6, and it gets brecciated and re-cemented and moved many times. And that's a very mature type of stage, which definitely reflects quite a bit of time. So what do we see in Palo Duro Canyon? Here's some features in Palo Duro Canyon where you see a lot of layers with nodules growing down in them, and a lot of nodular development on this, coalesced into these layers. Here's another picture of these where you're seeing, again, layers of caliche where it's cemented together, and then the softer clay rock has been washed out of them in this case. These are both from road cuts in Palo Duro Canyon. And to me, these reflect very well a lot of at least stage 3 of the calichification. It's fairly mature at that point. So you've had a number of layers of that type of maturity here. Well, let's go back to New Mexico. And in New Mexico, so what we're looking at here is pieces of caliche picked up on that road that I was showing you before. And we've got some very good examples of this piece of it. These little P-shaped and weird type of nodule in here. And this in cross-section, when they're cut through them, you can see lots of different layers of calcite. And in this case, they're pink. They've been concentrated with a little bits of iron in them. And you can see they're formed together. There's a complex water path that breaks up some of this and redissolves part of this area, and then it would form again, move it into some other part. A really advanced type of caliche development. What surprised me was this stuff is so hard and so well calcified that it actually takes a pretty nice polish. It would make a nice decorative stone, but instead of a road gravel, but it's quite variable across what you get. I enjoyed polishing rocks, so I thought this was pretty cool. Here's a couple of other pieces. Again, lots of these pieces in here. There's lots of layers of the calcite in those. And then on the right, you see a picture where you see some of the laminated rock, and it's been brecciated, and then pieces of it have been broken up, resubmitted. There's like a little white quartz pebble in here, but that's become really a part of the caliche time. What stage is that? It's a clear stage 6. It looks very much like what you would expect in a really mature type of caliche. This type of calification took a long time. It took a long time. Well, young Earth creation models would say that this took place in a very brief time. How long did it take? Most geologists would say that it took hundreds of thousands of years to form this extensive caliche deposit, with some of it being extremely mature, such as the pieces that we're looking at here. The X models have a real challenge to try to put an explanation of this. How would this Indiana-sized Paleosoil have developed over such a large area in just a brief time period? Of course, I'm not the first to think about this. Young Earth creation has also recognized that paleosoils are a problem today. Here's some of the explanations that they give. This is from a book called Rock Solid Answers. It's been compiled by Mike Ord and John Reed, both geologists. Here are a couple of articles by people who work with soil, and here's some of the points that they propose. First of all, it's important to realize that they would consider that all paleosoils would have to be after the flood. Post-diluvial means after the flood. And they recognize that you would not find them within the flood interval. Anything that's been identified as a paleosoil within the flood interval has to be something else. These forests that develop, and the places where we find some, particularly like some I'll show in another talk in Utah, where you had dinosaurs with all these tree roots around, had to have formed extremely quickly, and they could not have been paleosols. They had to be something else. Another explanation given is the rates of soil formation might have been much greater than today. And we've talked about how some soils can form quickly. But in order to do that, typically have to be very much more humid. So it needs to be warmer and wetter in the early post-flood time. But if it was wetter, how would you form a caliche? That calcium carbonate should have been moved completely out of the system in a wet climate. Another idea is that it's just faulty dating. Maybe all the indications that we have, such as from carbon dating, are completely wrong, and so this doesn't give us any time information. That's another problem which I think falls apart. What about when we find root traces like we saw in those in China? We saw them in New York. We saw them in West Texas, and we've seen them here. Maybe they were just simply buried upright. They could have moved by the flood and then just buried in an upright position. I doubt that the ant traces that we saw or the pieces that we had would have floated in the place. That just doesn't make sense for these. And I think it doesn't work for many places where we have paleosols found. Maybe they say caliches can be identified. So what we see in the rock record really isn't a caliche. And it's possible that there have been things called caliches in parts of the world that are not caliches. I don't think anybody wants to claim that the rock that we were looking at in the Ogallala Formation is not a caliche. I mean, it is kind of almost a tight case for that. Very, very good. And that's true in many parts, many places you find very distinct caliche deposits. Maybe the carbonate was formed syndepositionally. In other words, while the rock was being deposited, maybe it was deposited by groundwater. There may be cases where carbonate formed that way, but I think that's not the case in what we saw in the Ogallala Formation. And even if you did make that case, it still takes time. Moving that carbonate in and taking the material that was there before away takes a long time. It's not something that happens in a few days. Now, but they say that caliche can form quickly enough to clog drain pipes. Certainly, you can form lime deposits in a few years. We see that in New Mexico all of the time. You should see the lime that they pull out of some of the hot water heaters. But does that form a bed of caliche over a wide area? Can you really develop a Kansas-sized type of deposit very quickly that way? Again, these explanations to me are just not adequate. Now we're going to look in eastern New Mexico. We're going to look at the Blackwater Draw Formation. I told you that this provided some kind of mammoth insights into that. You know, it's interesting that here we begin to see human activity in the first time in the record. We don't find them down in what they would call the flood interval, but immediately after that, you begin to see these type of things right here in eastern New Mexico. For many years, this site between Clovis and Portales, New Mexico, was the oldest site where humans were found in the New World. Way into eastern New Mexico, which is kind of a surprise from my standpoint. You would think, well, maybe they would have been up in other parts of the world, up in the Northwest or something. But here was kind of a golden spike. And there are older indications of human activity now. But this is still kind of the gold spike for a lot of documentation. And I'll show you some of why. One of the things that's interesting in there is that you do find the mammoth bones, such as you see in the photo in the lower left, but you also see a number of other animals that are pretty rare in the area now. We don't see a lot of saber-toothed tigers. We don't see a lot of camels. We don't see bison today. Those mammoths are pretty special. Particularly found in the lowest part of this Blackwater Draw Formation. So let's look at some examples of where they're at. This is taken from the Blackwater Draw site at one of the exhibits they have there. And you see layers of bone. And the mammoths would have come from the very bottom layer down in this area. And then you see a number of things up above that. And that's what was really unique about this. Because archaeologists and anthropologists had recognized human artifacts from around the world, but they didn't know how to put them in order. For instance, you saw what are called Clovis points, named after Clovis, New Mexico, named basically from Blackwater Draw here. And you saw things that are called Folsom points, named after a little town in eastern New Mexico called Folsom, Midland Point, Agate Basin Point, a lot of different points, and you'd find each one at each location, you might find just one of them. And you didn't know which one have real clear indication of which ones were older than. At the time they were doing some of this, they didn't have radiometric dating to apply this way. So they had no indication of age, relative age. But here it isn't controversial. They're able to tell which ones are the older points and which ones are the younger points. So I'm going to take a look at a schematic cross-section through Blackwater Draw to kind of illustrate what some of the relationships. What we see is the Ogallala Formation at the base. Above that, you have the Blackwater Draw Formation, but in this area, you have the incised by a river channel. But the river's long gone. The river was also existed in the Ogallala Formation. But in this area, what you have is it filled in after the main river had gone away. and it's filled in with all of these other types. And included in them are some terraces, like the bottom ones here, which have the kind of the light blue arrow on it. Spear points are found in there and mammoth bones, and so this is where the Clovis points come from. Younger than that, you had what are called diatomaceous earth deposits, and in those, you got the Folsom points. Younger than that, you got these agate basin points, and then you got even younger than that, you got these other types of Paleo-Indian points. Okay, so we've got 4 different types of points reflecting 4 different cultures which developed, and you could tell that what order they were in. That was extremely valuable. The Blackwater Draw Formation included 5 different paleosols with roots preserved in them. Just point out again, so you have these Clovis points associated with mammoth bones. These are in what are identified as mammoth kill sites and butchering sites. That's cool. And then up above that, you have these Folsom points, such as this one here. And that's in a little bit younger. Younger would be these agate basin points. And then there's some other type of late Paleo-Indian points in here. And you can tell the age on those. So now we have radiocarbon dating to use. And radiocarbon dating tells us that the Clovis points were around 12,000 years ago. The Folsom points were 10,000 years ago, and a series of ages after that. It's not very obvious, but those are ages don't fit the young Earth creation time frame. So we'll look at those to drive that point in a little more clearly. Okay, just to drive home the point, how fast things would have had to work in the young Earth creation model. Let's imagine that again, we're going to throw out all the radiometric dating, no particular justification that way. Young Earth creationists will accept radiometric dating when it tends to support the Bible, but when it doesn't support their interpretation, then they want to throw it out. So let's just say we're throwing it out, and we're looking here again at the Ogallala Formation, 30 days of deposition, maybe 200 years, depending on which model you're accepting. So we've got the Blackwater Draw Formation. The top of it has a pink line across it right now, and it might represent maybe 450 years to deposit some fill of the old stream system with all of the paleosoils involved in it in the ICR model, but maybe 90 years at most, perhaps using Dr. Snelling's thing. And then we have the 4,000 years of deposition above that. Let's kind of give some calibration on that. So again, from my standpoint, I would say that all of the cultures of Indian artifacts had to be formed, before the time of Abraham for a very short period of time. There's a friend, Kevin Elstead, who is a geologist and a geographer, says, except the problem is too many events, too little time. We just have too many things to reconcile, too many things to try to fit into just a little bit of things. So there's one other part that I want to take a look at. So let's go beyond this one step and let's say, well, where do they get the material to make these arrowheads out of, these spear points? So let's take a look at that. And for that, we're going to go back into Texas. So we've got all of these points on here that are made from something that is solid and hard. It wasn't made from something soft and mushy. That had to happen in some way. There's had to be a time frame when it hardened. I don't think that Abraham used something soft and squishy whenever he was circumcised. Typically, they had flint knives. A lot of what we're looking at here was flint, and some of the key parts of this would have come from a place near Amarillo called the Alabates Flint Quarries. And the Alabate Flint Quarries are there near what is Lake Meridian today. And you find that the Clovis man and the early Americans had a favorite stone from which to make their treasured points. Some of them came from this site. And this is an example of the type of rock in the picture here. And what you can see is kind of the top of a mesa there. And back behind that, you would have these quarries where the ancient Indians, Paleo Indians, would work. So here's a couple of examples. These are examples of the rock material that they were using. A piece of shirt from the Alabates flint quarries that is comes from online. And then there's a piece on the right that is a piece that I've cut and polished. This was given to me and was collected well before there was a national monument in this area. This was when it was possible to collect that from one of my professors in the school that I went to. You can see that the material has been brecciated, been broken apart, been re-cemented into a solid rock this way. You can see that some of the bedding within it from the original rock. And there gets to be an interesting story for how this came to be. At least it's interesting to a geologist. Let's see what you think. The Alabates flint comes from the Alabates member of the Quartermaster Formation. We saw some red beds of the Quartermaster Formation that was Permian in age earlier. We saw that in several places. So the red beds have certain units within it that were made up of dolomite, and those included the flint. Flint became something that the Indians could work with, and it was hard and it was beautiful that way. And when you have a material that you can do that, it's called napping material. And there's other napping material that's up considerably younger than this. Another favorite material comes from the flints in the Cretaceous period. And there's even some in the Ogallala Formation, although that wasn't a favorite of theirs. And then you can see where Clovis man would have been right up at the top. So he would have been very young in this type of picture. So how did they form? As a geologist, we can identify a lot of different steps that took place. You know, that flint wasn't originally deposited as flint. It was deposited as lime muds. They were settling in a section of rock that has stromatolite. It has these algal mats in it and hydrite. And so you would expect that it was deposited in an arid type of setting, something like the Persian Gulf. Over time, that lime mud was replaced by dolomite in these ancient brine pools, similar to what happens in parts of the Persian Gulf today. And then that section was buried. It was covered by the Ogallala Formation eventually. And then that dolomite, parts of the dolomite were replaced by silica. When did that take place? This would have taken place during the time when that caliche was developing. You can tell that by the fact that the flints are often associated with the section immediately below some of the caliche. And it's often stained red. It's stained red from iron, which came filtered down at that time. The silica had to be hardened. That takes time. That silica was hardened to something that's basically an agate. You can call it a flint, you can call it a chert. It's a very fine grained, very even, beautiful type of flint, which can be considered basically and oftentimes almost a translucent agate. But if it's down in the rock like that, that would never have been made into arrowhead. It had to be eroded away. So it had to be uncovered. And erosion had to reveal that, but it came through that caliche with time. And then the Paleo Indians found it. They dug pits around so that they could excavate it. They would nap it. They would break it into these blanks, and the blanks could be traded over a broad area. Then people could take those blanks. They could nap them into whatever type of arrowhead that they wanted to make, whatever type of spear point, whatever type of feature they were trying to make. A lot of different steps. From a standpoint of a flood geology, to me, it is, again, too many events, too little time. How long did it take for silica to harden to agate? We would expect that it would have taken thousands of years. Thousands of years is a problem if you believe in the flood geology timeline. Okay, we're going to try it again. We're going to look at the flood models and then draw a few conclusions at this point. This is again a timeline that's vertical with the oldest at the bottom. And again, we'll see that on the far right, you see Clovis man and Folsom man and the Paleo-Indian period, and then that was followed by the Archaic period. And conventional dating would say that that Paleo-Indian period ranged from about 9,000 BC to 6,000 BC, way before the young earth interpretations of the flood. And you can see that it's not the only type of site. If you were to go back into, for instance, Turkey, you have an ancient temple, perhaps the oldest temple that has been located, and that formed about 10,000 BC. But there's a number of different cultures which would fit in above that. For instance, in Mesopotamia, you see these type of cultures which range from apparently 4,500 BC up again through the flood period, but it went away before the flood happened. Then you would have ancient cultures in India, ancient cultures in China. You have the Egyptian pyramids. What were they made out of? They were made out of hardened rock, right? Then you have Stonehenge. Stonehenge would have been formed before the flood, and it was made out of hardened rock. When did all of that happen? One thing apparent is, regardless of if you tried to collapse all of this into the time immediately after the flood, man was spread out over a very broad area very early. And that gets to be another interesting kind of problem from a flood geology standpoint. So let's imagine that Noah stepped out of his boat in Mesopotamia. What would that have looked like? We have a map of the earth, and I just dropped in a triangle from Mesopotamian area where we would believe that Noah's flood took place. And then we're saying that almost immediately afterward, if not before, that we have Paleo-Indians in eastern New Mexico and West Texas. How about that? How does that work? Man had to migrate extremely quickly that way. We believe that man did migrate from that type of region all across the globe. And we see that they eventually did come into eastern New Mexico from that area. But surely that took some time. Did people get out of the boat? They had to have kids. Did those kids then, few of them, move immediately out across all the way to eastern New Mexico? Hard to work that out. See, throwing out carbon-14 doesn't make the problem go away. It's still a problem that way. Things have to have happened extremely quickly in this type of model. Carbon-14 is a valuable technology, and it gives us a lot of great information in stratigraphy. It's only used for certain time periods, so down back to around 40,000 years ago. But still, it's a very valuable thing. And even if it went away, we would still have the same thing. So in this talk, just to kind of give you a list of kind of the issues that, from my standpoint, the flood geology needs to provide answers for. One question would be, how do you form soils during a flood? We saw examples of rock in China, from New York, and from Texas, where we saw well-developed soil in rock that flood geologists all interpret to have been during the rising part of the floodwaters, early parts of the flood, and they're well-developed with trees and indications of soil. How does that happen? And it's not just that they are soils, but in many cases we find arid or semi-arid soils that apparently would have formed during the flood. How do you form a caliche during the flood? How do you deposit extensive caliches in a short period of time, even if you're saying that it was after the flood? How do you form caliches over an area the size of Indiana? How do you get humans to the Llano Estacado right after the flood? And if you do get them there, how do you harden flint for arrowheads in time for the humans that got there right after the flood? What did Abraham have to use to cut with and to make weapons out of? What about his parents, his grandparents, his great-grandparents? These are the type of issues that we see over and over in flood geology. Again, I want to make the point that the failure of young Earth creationism, young Earth interpretation says nothing about Christianity. It's really just about that particular interpretation. It tells us that that particular interpretation doesn't work, but And you really can't interpret the Bible and then try to force science into it. Not a case of the Bible being wrong. Because, for instance, nowhere in the Bible does it say that the earth is 6,000 years old. Nor does it tell us what sediment was laid down by Noah's flood. That's just not in there. Use an example. I like the work of Oxford mathematician John Lennox, and I listened to an interview of his on his book, 7 Days That Changed the World. You can search for that online. And one of the things he points out is that there was a time when most people believe that the earth doesn't move at all. It's scripture. Scripture says that the earth doesn't move. It also fits their observation. When you drop a rock off of a building, it falls straight down. But if the earth was moving, you would think it would have been offset that way. But that's not what's happening that way. It made very good sense from them from the standpoint of what they observed. Most of us believe that the earth does move. I do. I don't have any problems with that. Over time, theologians came to the understanding that believing that the earth moves doesn't really impact our belief in the truth of the Bible. Those parts of the Bible could be interpreted more figuratively, and it did not change their meaning, and it did not change the historicity or accuracy of the Bible at all. Hopefully, in time, the same will be true regarding the date of creation and the extent of Noah's flood. That's what I have for you today. Thank you for listening to this point. If you survived to this point, I hope you found it useful. I'd love to have comments and feedback, so please feel free to drop in on my webpage, send me an email, write a message on there, write a comment. Thank you very much.